So this started with trying to build some kind of bridge between the community of cold atoms and the tensor network community. But then suddenly, like 4 papers came up, like doing similar things with Gross-Pitaevskii equation during sometime in July of 2025. So we've just seen one of them. This is another one. And yesterday or 2 days ago, we saw another one, I believe. So, okay, this was meant to be kind of pedagogical because it was the whole reason of the paper to introduce the cold atom community to these type of simulations. But well, I can speed up things because, okay. So these are my collaborators. These 2 are basically in Madrid, and Marcin is in Barcelona. And we have been doing like joint work. Basically, Marcin is the expert in GP, and we have been implementing the tensor network stuff. Okay, so the idea, which all of you already know, is that tensor networks basically were introduced to represent exponentially large tensors just by dividing them with smaller tensors and doing some contractions at some point when you want an operator or whatever quantity you may want. Okay, and again, this was pioneered in the context of many-body physics. Then it was rediscovered by mathematicians, as long as I know, but maybe it's the other way around. I'm sorry if that was not the correct ordering. Okay, so, okay, Quantics Tensor Trains, I will use Quantics Tensor Trains and matrix product states similarly. I know that they represent kind of different things where one is basically discretizing a real function and the other one is representing a wave function of many-body physics problem, but I will interchange sometimes because of, well, I'm used to talk about matrix product states. So, okay, they were basically introduced to efficiently represent ground states of gap Hamiltonians, and then they have kind of been evolved over the years to do other things. Now, for one of those, for example, was this new community, the Quantics Tensor Train community, where you take a real function or an analytical function in a domain, and then you do the usual thing you would do with a vector, which is basically discretize the domain. Naively, you would do in a homogeneous grid, and then evaluate the function in the homogeneous grid and put it on a vector, right? I'm sorry, Jason, because I know that's probably, there are better ways to do it classically. But then the idea is that the cost of that is O of n, where n is the number of discretization points that you have. But if you put it on an MPS, presumably you will have a log, the cost will be log of n, but then you will have an overhead which depends on chi. So if chi scales exponentially with your number of bits, then you don't have any type of improvement. So that's the point. Okay, then there is some kind of generalized version where if the QTT is a version of a vector, then you have the matrix product state, which, as far as I know, in this community, there is no name for an MPO. Okay, yesterday night, some proposed some kind of new names, but they are not set in yet. So the idea is that the generalization of a matrix is basically a matrix product state, and I just wanted to highlight the cost of multiplying QTT with an MPO, which is chi cubed times q plus chi square times q square, where q is the bond dimension of the MPO. Okay, so this will be important at some after when we talk about nonlinearities. Okay, so now the Gross-Pitaevskii is basically a non-linear Schrodinger equation, and it has been successfully used to model different type of Bose-Einstein condensates. Okay, and the simplest version of it is basically this thing where you have the Schrodinger equation here, and then you have this nonlinear term. Usually the interaction is repulsive, but there are some times that you can turn it to be attractive. Okay, okay. Then there is some generalized versions of Gross-Pitaevskii equation, starting by, for example, long-range interactions, okay, where basically you assume that there is some kind of Milfin approximation of a two-body interaction and follows this type of form where you have some kind of potential here that acts in a place X, but it depends on the density in position X prime, okay? And then there is also another equation that we have looked at, which is the coupled Gross-Pitaevskii equation. The idea is you have several species of a Bose-Einstein condensate in the same place or in the same harmonic trap, in the same microscope. I think this is beginning to be realized like now in the microscopes that they have in Barcelona, for example, at ICFO, where you have several species interacting together. So basically you have now, instead of a single particle, well, a single density interaction, if you want, now you have two different species, and then they can interact between each other, but they can also tunnel. So they can change, because sometimes it's the different species are just different spins that they have, so they can tunnel from one type of species to the other. Okay. Okay. So basically, what we need to represent to solve the Gross-Pitaevskii in QTT is the different the linear operators, which are basically the wave function and the linear Hamiltonian. This it has been done, and it's fairly easy. Then you have to represent the nonlinear term, which there has been, I believe, several talks about that. Then if we want to introduce long-range interactions, also the long-range interactions, and we have to generalize all of it for different BSC species, okay? Yeah, so the toolbox that we have is, well, loading functions can be done in several ways. Basically, this, I believe, is a conference that deals about that, how to encode functions into the QTT, which usually you can do it by either cross-interpolation or Chebyshev interpolation. There are some times that you can do it by hand, but there are so few examples that it's not worth, because saying them. So then if you want, for example, to put a local potential, you can basically encode the potential with either one of these methods, and then use Kronecker test to update it to the MPO. Okay, then in this talk, there has been several talks about how to do this type of band diagonal matrices, and if you have to multiply them several times to shift the diagonal upwards or downwards. And again, it has been also discussed that this can be done by basically creating already the MPO with Pauli matrices, right? But now I will introduce you a new algorithm. I mean, I believe it's nice to know it, but probably most of you have already realized that this can be done, which is basically, so the idea is you want to create f of x minus a from f of x. Okay, and this can be done through this ripple carry algorithm. Okay, so if you binarize your A, then basically you have two possibilities, that A is equal to 0 in a particular site, or A is equal to 1 in this particular site. So the main idea is that to perform the sum from the bottom to the top, right? So this index here basically will label if we carry a unit from the previous addition or not. And then we will basically sum the unit that we are carrying plus the bit if it's 1 or 0, plus whatever AI is. It can be 0 or 1. Okay, and then this will fully resolve the whole tensor, because PI and LT will, this will basically indicate if we are carrying a unit towards the upper tensor, and this one will indicate basically if the result of the sum is 1 or 0 modulo 2, right? So basically, this is how you can create these tensors. There are only 4 possibilities which are non-zero, and then you can create this tower and basically have this translation operator. The only thing that's missing here are the boundary conditions. So from the bottom, you always put 1, 0 because you don't carry any type of unit from the beginning. And then on the top, you can either put 1, 0 or 1, 1 if you want free boundary conditions or periodic boundary conditions. Okay, so that was good because now we will have to create a function which is from f of x, which is f of x minus y, basically for the long-range potential, right? So what we can use is basically this same setup, but now instead of labeling AI 0 or 1 because we have a fixed A, we lose this fixedness of the A, and basically we can add a new leg which tackles this A. Okay, and this will create basically some kind of generalized MPO with only bond dimension 2 that in fact exactly does this correspondence from f of x to f of x minus y. Okay, so that's what we will do with the long range, but then again, now the differential operator is very easy to create. It has the exact same bond dimension and the exact same, it is the exact same differential operator that it has been introduced with polymatrices, for instance, but it's a different way to realize it. Yes, and then we are here to deal with the nonlinearity is one of the things that we have to deal. The main problem with the nonlinearity, as it has been shown in many talks now, is that you have to deal with this chi-fourth. So I know of this, or at some point, 2024, this paper came out that said that they were able to speed the multiplication, the tensor train multiplication from chi to the fourth to chi to the third. But the main problem when I implemented it, and maybe it was just because of the range I was using, it was not the correct range of TT multiplication that they were planning on. I have this kind of entanglement barrier almost where as you go through the algorithm, the bond dimension grows, and then it goes down again when you have all the bits in the correct order. So in the end, in my case, the efficient way to perform this nonlinearity was basically put one of these wave functions as an MPO using delta functions and then contracting MPO QTT, which scales like that. But well, now with Miles' algorithm, maybe we will improve this part. Okay, then one of the last things that we need is basically the long-range potential. The long-range potential, we already have all the ingredients to create it. So the first ingredient, the first thing that we have to do is load this potential shape with your preferred method, TCI, Chebyshev, or whatever method you want. Then we basically use what we call this convolution operator, which basically creates this W of x minus x prime. And then we perform this MPO QTT contraction with the actual nonlinear term that we will have computed because we have to compute also the nonlinearity. Okay, so with that, the only thing missing is how we interpret these multiple Bose-Einstein condensate species, right? So the idea in the vector, or the traditional idea, is basically to encode the different species in several vectors, right? And that's it. But now that we have these new algorithms or these new representations, we can encode the different species in different bits here, okay? So basically, we are labeling each species for a number from 1 to m, and then we can represent it as a binary in the usual way that you can do it in 2 dimensions, for example, x and y. So it's very similar. So now the idea, sorry, is that we have to transform all the formalism to deal with these different species, okay? But this is not difficult because you have to, well, you go through the equations and you realize that everything decouples. So the species and the spatial bits completely decouple in all the operations. So the local Hamiltonian obviously only acts on a single species at a time. Then the tunneling term, it's the other way around. So it doesn't change at all the shape of the function, but it can swap one function from another, okay? The only difficult thing is to create this, is to create this MPO lambda from the tunneling matrix. But as long as there are some correlations between bits and you order them correctly, you can load it using TCI. For example, it's trivial if the tunneling decays exponentially. For example, this is an MPO of bond dimension 1, but there are several examples where you can basically load this matrix using TCI. Okay, and finally, the last term, the nonlinear term, also decouples because basically there is some kind of not interaction, but some kind of term that basically will switch and perform the summation over all the possible species, but then you only change, but then the nonlinearity, this phi square, it's with itself, it's with the phi itself. So these only modules the different species that it will interact, okay? So basically this operation also decouples, and you have your usual delta functions with an additional MPO here that again can be learned using TCI, okay? So now I will go through the algorithms I've used to reproduce some of the results, which are pretty easy. The first one is just a time imaginary evolution that matrix vector multiplication would do. Okay, so basically we trutterize this type of expression, okay, and then we iteratively find this ground state, okay, until we converge to some epsilon in energy, okay. And then for the time evolution, I've used the Runge-Kutta 4 method. I've used this one basically. I know there is some talks about how to evolve it using TTBP or things like that, but I wanted to be able to compare it with methods that the community, the cold atom community is used to. So basically, I wanted to show this community that you can actually do all the same operations that they are used to with these methods, right? So the idea is that you can implement a Runge-Kutta solver using QTT, basically by finding each one of these K1, K2, K3, and K4, and then you can look at the new time-stepped wave function, okay? And now I have some several applications. I'm not sure how I'm doing one. Okay. 5 minutes. Oh, great. Okay, great. So then the applications are more or less easy. All of them are in one dimension. So that's why the bond dimensions that you will see are not very large. So the first one is basically look at the ground state of a double well potential. This is the potential that we have used. Maybe this is not exactly a double well because we have this exponential instead of a quartic term, but whatever. Okay, and these are the results. So this is for a non-interacting Gross-Pitaevskii equation, which is the Schrodinger equation. We see that for k equals 0, we basically have a Gaussian packet. But for g equals 1, what we see is basically that the wave function is way shallower and wider because there are repulsive interactions in there. Okay, and then you can see that the L2 error of both cases is kind of small, almost beyond machine precision, and you are able to compress properly the functions.
How many bits?
9 in this case, but because the Gross-Pitaevskii equation, or in traditional methods, the Gross-Pitaevskii equation gives you already with the parameters the number of discretization points that you need with the correlation function. So when you look at the correlation function of your Bose-Einstein condensate, I believe you can know how many grid points you will need for this simulation. At least in these simple cases. In 2D, I'm not claiming that, but because I'm not an expert. But yeah, 9 bits for this case. Then we have looked at the long-range potential, and it was really similar to the previous talk, where we are basically looking at breathing oscillations. Okay, so the idea is that you have a Bose-Einstein condensate. When you turn your tweezer array on, basically you induce long-range interactions on this Bose-Einstein condensate, and these interactions follow this type of shape. And then, as long as the radius of the Bose-Einstein condensate is smaller than the blockade radius in this Rydberg array, you can basically go to this mean field approximation with nonlinear potential. Okay. Okay. So to measure this, our collaborator Marcin wrote a paper, which basically the idea was to measure these interactions in a twofold scheme. The first one was to prepare a ground state in an harmonic trap, but with the lasers, the tweezers turned on, okay? And you let the Bose-Einstein condensate basically settle down or to find the ground state, okay? This is for different interactions. And then the lasers are switched off and you let the system evolve. It's just a quench. Okay, and the idea is that the frequency of the evolution or the frequency of the oscillations of this Bose-Einstein condensate do not depend on the interaction term. Yeah, exactly. Do not depend on the interaction term. It only depends on this term beta here. And then the amplitude only depends on the interaction term. Okay, so we were able to basically measure standard deviations, which is an easy task to do with QTT. And we saw precisely that our frequencies are exactly the same for any type of interaction. Okay, and then we can also look at the errors that we are committing within the wave function and in the observable, and we can see that are pretty mild for a cutoff of 10 to the minus 12 or a bond dimension of 8. So for this type of cutoffs, in fact, you don't get much of a optimization in memory, but for chi equals 8, the memory is already there, similar to what you have to store with matrix vector multiplication, where you have to store a matrix and a vector. Okay, and this is for 1D, so it's nice. Okay, and then the multiple species, we have a little bit of a struggle because we did not find many interesting papers to reproduce that, right? So we only have one example of that, which is basically we have a quench of this initial state of a change, okay, with some momentum, and then we have these several species interacting between each other. And the results are here. They agree nicely with the matrix vector results. But again, we are still struggling to find some applications for this method because, there are not much interest, it seems, to having like an exponentially large number of species in the same Bose-Einstein condensate. Although I have to say that this new microscope we have been in talks because they seem to have like 8 species, which is not usually done with vectors and so on and so forth. So with that, I thank you for your attention, and I'd be glad to.
Okay, we have time for questions.
I have two. One is physics. Can you go back to your Rydberg atom slide?
Yeah.
Something I missed, like
this one?
Yes, no, this one. So you said that if the radius of the BEC is smaller than the blockade radius, you can actually. Are you sure it's not the other way around?
Okay. So I'm not the expert, and I may have missed that. But
because I mean, I mean,
well, yeah,
how
it's
do you
very
want-
small. Exactly. Yeah, I
they
agree.
they are just you cannot put that.
Yeah. Probably it's the other way around. I just got confused when
Are
translating
you
it.
sure it exists like this regime? Because that means very because
Which one? The smaller or the larger?
I mean, are there BECs of Rydberg atoms? Because
Well,
so because the radius of a Rydberg atom is typically like there are
no. Okay,
right
yeah.
rounds.
Maybe what I'm saying is maybe I'm wrong with that, and I basically got confused.
That's probably.
Yeah.
But in addition, supposing it's the other way around, you want to make a condensate of atoms that are where the core is a micron wide. So it means that the condensate would be like, I don't know, like millimeters or so to be in a mean field regime.
Okay.
I don't know. I don't know. I mean, I know a little bit the Rydberg.
I think because also, okay, these all these microscopes that I am talking about, I think they work with. So the idea is that they have a Bose-Einstein condensate, and they are able to shine. So they are able to see what the condensate does. So there must be some regiming where the Bose-Einstein condensate is in the Rydberg. I can send you references if you want.
I would be interested.
But maybe I have something wrong in that, and if I have, I'm sorry about that.
Yeah, I think it's.
Yeah.
Second thing is, so the same question I had for Chamin is that so you studied like a regime with small number of bicarbonate, and it's pretty clear that this kind of techniques are not going to shine in this regime.
Exactly.
Yeah. So did you try to push just to see if technically you could do it?
Yeah. So okay, there are two things. The first one is we at some point we did not want to go to dimensions for now because we wanted to showcase just some toy examples. Okay, and I completely agree with you that this probably will not shine in one dimension, and even in two probably will not shine, right? So the thing is that you need so many qubits, if you want, or so many sites to beat traditional traditional methods that probably the only way to beat them are
Has to be bigger than 1 billion.
Exactly, and then the problem in one dimension is that you can always go there, but there is no reason for, because again, all with the parameters you have in your experiment, you basically know how many grid points you need, and usually in one dimension it's not more than 1,000 or 2,000. Okay, but yeah, no, I completely agree that we should be pushing for 2-1 3D, and in fact that's what we want to do. Yeah.
Other questions from the audience? Oh, okay. So the question from the chat. Okay, so the question is: did you check norm and energy loss in your time evolution due to QTT truncations? So basically, do you normalize every step?
Okay, so yes, I believe I renormalize the norm each step. What I do not do is check energy, because basically we are implementing a Runge-Kutta-4. So the idea is that the energy loss will correspond to the Runge-Kutta-4 method and not to the QTT method. But maybe we are losing more energy than we should with the Runge-Kutta-4. No, we have not checked that.
Any other questions from the audience? Okay. No other questions on the chat?
Okay.
So he's typing. Okay, not for now. Okay. No applause.
Thank you very much.
Okay, let's think.